Hello, we are grateful to be virtually present at the International Conference on New Horizons in Education being held in Rome these days, presenting the paper Learning Objects for Numerical Analysis Courses. We are Marta Caligaris, Georgina Rodriguez, and Lorena Laugera, and we belong to the research group INT-E, Spanish initials for Engineering Education Group. This group works on the San Nicolas School from the National Technological University from Argentina. We all teach numerical analysis in engineering careers at this school since year 2006. We have been developing a virtual lab for numerical analysis, that is to say, a collection of customized applications for teaching our subjects. They were developed taking into consideration the learning style of the students. We detected, by means of surveys, that our students are most visual and kinetic in the neurolinguistic programming classification of learning styles. The tools developed by us can be considered as learning objects. This term was introduced at the beginning of the 90s. Many authors have defined this concept in different ways, but one of the first established and widespread definitions is that given by Wiley in year 2000, who considers that a learning object is any digital resource that can be reused to support learning. In order to ensure quality in the development of learning objects, a number of properties have been established. Learning objects should have the following characteristics. Digital format. Learning objects have the ability to constantly update and/or change. Learning objects are used from the Internet and they are accessible to many people simultaneously from different locations. Educational purpose. The purpose of learning objects is to ensure a successful learning process. Other property is interactive content. Learning objects involve interactive participation of each individual, teacher or student, in the exchange of information. Thus, it is necessary that learning objects include activities such as exercises, simulations, diagrams, videos, graphics, etc., to ease the assimilation process and track the progress of each student. Independent and indivisible is other property of learning objects. They must make sense in themselves and be self-contained. Furthermore, learning objects cannot be decomposed into smaller parts. Reusability is the last property. It means that learning objects must be able to be used in educational contexts other than that for which they were created. Reusability is the most important characteristic of learning object. For example, we use our lab in class, but students also can use it at home for studying the issues of the subject. The design of a learning object is a real challenge for teachers because, besides choosing the content, they should create the appropriate ways of its presentation, depending on the characteristics and learning styles of the addressees. From the technical point of view, what we made are graphic user interfaces. In other words, window applications developed in mathematical software that allow using the calculation and graphing power of it in a friendly way, without worrying about the commands needed to get the solution of the proposed tasks. For example, programs that have the capacity of making these are Maple, Mathematica, and MATLAB, and also Scilab is other software. Scilab is a free software that can be downloaded from the website www.scilab.org, but the others are commercial. We are working out in our virtual laboratory of numerical analysis since year 2007. It is made of a collection of applications for different issues of numerical analysis, originally developed in Maple But for reasons of accessibility of the software for students, we turned out to develop the windows in Scilab since year 2010. The topics of numerical analysis involved in this laboratory are the following: nonlinear equations, systems of linear equations, systems of nonlinear equations, interpolation and curve fitting, numerical integration, and methods for ordinary differential equations and partial differential equations. We describe here tools available for these issues. For nonlinear equations, we have developed a window that looks like this. Let's see this window in action. Here you have a box to charge the function and its derivative if you are going to use the Newton method. At the right you have an interval to charge so as to get a graphic of this function in order to estimate the root you will find. You need to put the data for doing the calculus, that is to say the number of iterations permitted and the allowed tolerance. In order to apply the bisection method, you will have to charge an initial interval, and by pressing the button calculate you will get the approximation and the number of iterations required. If you want to apply Newton's method, you will have to put an initial point, and pressing calculate you will also obtain the approximation and the iterations needed. For the other two methods you will have to put an interval, and by pressing calculate on both sides you will have the approximation and number of iterations required too. As you can see, all the methods were applied for the same function, and you can compare the approximations obtained by each one. Another window we developed was that for numerical integration. Now, let's see that window in action. Here you have the box to enter the function you're going to integrate and the interval where you are going to make the integration. Then you can have a graph of the function, and at last you have to put the number of intervals or number of points of each method. Pressing calculate you will get the result of each method. Now we show a tool for ordinary differential equations. We have another window also that implements methods of one step. Here we show multi-step point methods. In this window you can solve first or second order points. If you choose second order, you will have the box necessary to enter all the data for this kind of problem. By choosing first order, you have to enter the differential equation you are going to solve, the interval where you are going to get the solution, and the initial condition. If you want, you can charge also the law of the exact solution, so as to compare results. Then you have to choose which methods you are going to apply. You can apply up to 3 methods, and they can be the same or different methods. If you choose the same methods in the 3 cases, you can put different number of points to compare. Pressing the button graph, you have the graph of the exact solution and the points of each approximation made. The last window we are going to show here is that for systems of first order differential equations. Here we apply one-step methods. Let's see this window in action. Here you have to enter the two differential equations and the interval where the solution will be obtained. Also, you have two initial conditions, one for each function, and you can also put the exact functions solution of this problem so as to compare results. Then you will have to choose the number of methods you are going to apply by clicking in each box, and then you choose for each color the method you are going to apply. At last, you set the number of points for each method, and then clicking the button graph, you will have the graph of the two functions that make the solution of this problem. By clicking View Results, you can get a table with the numbers of the solution. Since their creation, the different tools that constitute the virtual lab of numerical analysis have been used in numerical analysis courses in the Facultad Regional San Nicolás, and they have been well received by students. The use of these tools, both in lectures and practical classes, can generate new learning spaces where it can be promoted interactive engagement of students with the content of the laboratory, thus enabling the understanding and learning of the issues involved. Usually, different examples, properties selected, are shown so students can easily understand certain concepts, as well as analyze the advantages and disadvantages of each of the numerical methods studied. The teacher's role in this context is to provide, through the design of teaching sequences, a meeting between the student and the environment for the emergence of knowledge. It is in the interaction and experimentation when the student understands deeply the concepts to be taught. Conclusions. Any professor interested in the learning process of the students must recognize when difficulties arise in teaching. By studying the learning style of students, good basis can be obtained for developing teaching strategies in line with the habits of the students. Based on the study in numerical analysis courses at Facultad Regional San Nicolás, visual applications like those shown here were developed to let students interact in the process of incorporation of numerical methods, allowing them to analyze results instead of wasting time with tedious calculations. We consider the design of teaching sequences supported by these tools is an alternative for students to build a comprehensive and meaningful learning, managing to interest students in order that they can find meaning and taste the experience of learning and actively participate in the process of acquiring knowledge. Thank you for your time. We are the Engineering and Education Group from San Nicolás, Argentina, and this is our mail.